We're going to talk about inhibitors, and we want to start with competitive reversible inhibitors. And we're going to return to the Michaelis-Menten model to show you a little bit about how this works. Remember that the Michaelis-Menten model has an enzyme and a substrate coming together, being mixed together. They bind to each other and form the Michaelis complex, where the substrate is fit into the active site of the enzyme reversibly, and it can then either go and become product through a chemical reaction and get spit out, or it could theoretically unbind and become free substrate again. So let's just say this again. This side is about binding, and this side is about chemistry or catalysis. That dual nature of enzymes is still with us. So let's consider the nature of a competitive reversible inhibitor. To describe it, let's jump down and fill in the blanks of our third line here. I see there's a little mistake there. This should be I for inhibitor. And in a competitive reversible inhibitor, the inhibitor binds in the active site. In other words, it binds in the exact same spot that the substrate binds. So let's go up and consider what that's going to look like in the case of the Michaelis-Menten model. So let's consider what would happen if we mixed enzyme and substrate and inhibitor all together at the same time. The enzyme can bind to the substrate, like we talked about before, in a reversible manner, or it could bind in the other direction with the inhibitor and form a reversible complex with the inhibitor. We'll call that E.I in a similar manner to what we said about E.S. The key for a competitive reversible inhibitor is that you have to go one way or the other. Because they bind in the same spot, substrate or inhibitor can bind, but not both at the same time. In other words, we can't have the addition of inhibitor to form a triple complex like this. This is simply not going to happen. Nor can we have the enzyme inhibitor form and then add substrate and hope that we're going to form that triple complex. This is simply not possible. It's a choice. It's kind of like musical chairs. Only one molecule can fit in that active site at the same time. So what we're saying is that the inhibitor is truly going to affect this side over here. It's not going to affect what happens after the substrate binds because the inhibitor and the substrate can't be bound in the same place at the same time. So the only thing the inhibitor can do is prevent the substrate from binding. Now what that means is it's going to affect one of these two values down here, Vmax, which is really essentially the same thing as Kcat, or it's related to Kcat, or Km, which is here. Now, I want you to think back to what we discussed before and ask yourself, what does Vmax and Kcat focus on? Is it this side over here in the chemistry, or is it this side on the binding? Same thing for Km. Is it binding or is it chemistry? And let's decide what you think is going to happen to these values. Are they going to go up or down or stay the same? Pause for a moment and see what you come up with. Okay, so I hope you had a chance to think about that. The inhibitor prevents the substrate from binding. In other words, it makes it harder for substrate to bind. And what that is going to do is it's going to make it appear that the substrate can't bind as well. And what that means is the Km is going to be higher. Remember we said a higher Km is an indication of worse binding? Well, if you got somebody trying to compete with you getting into that site, it's going to be worse. However, what we can also say is that the substrate to product conversion over here, the chemistry, that's all reflected in Vmax and Kcat, and that's not affected at all by the inhibitor. So in that case, we're going to have no change for the Vmax. So let's go down and take a look at what our kinetic plots are going to look like. Let's see what a direct plot, velocity versus substrate, and an indirect plot, 1 over velocity versus 1 over substrate concentration, is going to look like. What I've got here are dotted lines. This is the absence of inhibitor, and that's true over here as well. Remember, there's real key things along the way. We got KMs and Vmaxes and things like that. And I already told you above what is going to change in the presence of a competitive inhibitor. So pause for a moment and let's see if you can fill in the curves that you would expect to see for in the presence of a competitive inhibitor for both graphs. Okay, we start up again, and let's remind you, Vmax is here, Km is here. In the absence of inhibitor, that's what we're going to see. But in the presence of a competitive inhibitor, we'll do this with green, we would expect to have the same Vmax, but the Km would be higher, that is, pushed to the right. So it might look something like this, where we still level off at that higher value of Vmax, but we're going to push our Km out in the presence of inhibitor. So this is going to be the line that you'd expect to see in the presence of a competitive inhibitor. Same Vmax, higher Km. Okay, did you try it in the case of the Lineweaver-Burk plot on the right? This is super tricky, and we're definitely going to practice this on the homework. In class, I would sometimes put it this way. We are going to have a straight line, and it's going to be passing through the dotted line, that is the no inhibitor line, at a certain point. And I'd ask you, where do you think they're going to be identical values? Where is the line going to be the same? Where's it going to cross? And the answer is, we said the Vmax is the same, and therefore the 1 over Vmax should be the same as well. So these lines are going to be non-parallel. They're going to cross at this x-axis, or rather y-axis point right there. There's one other trick to this, and that is, if you put an inhibitor in to an enzyme substrate reaction, it lowers the velocity. What would it do to the inverse velocity if it lowers the velocity? The answer is it would increase it. So that's a really tricky part. Here's the answer for the plus inhibitor. It's going to be a straight line because we are inverting a hyperbola just like we did before. It always ends up as a straight line. It passes through the same point on the y-axis right here because it has the same 1 over Vmax and therefore has the same Vmax. Lastly, it has a different Km, a different 1 over Km. It actually has a 1 over Km that is closer to 0. It's closer to the origin. That sounds like it's smaller, but remember, it's the inverse Km, and a smaller inverse Km is actually going to be a larger Km. Okay, one last thing about reversible competitor inhibitors, and then we're done. And that is, because they bind in the same spot, the substrate and inhibitor both bind in the active site, we can say that the substrate and inhibitor often look similar to each other. Does that make sense? If you've got two things that are going to fit into the same site and be complemented by the same chemical structure, then they should look chemically similar. And that's why a lot of enzyme inhibitors that are drugs are going to look very similar to molecules that are in our body that are natural substrates for enzymes. All right, let's put that aside and pick it up with a different case of non-competitive inhibitors on the next page.